Okay, I am recording now, and today we're going to speak about PV panels, and we're going to explain the fCHART, this new software. Okay, so we will be working with this software, but remember that we can work with PV watts. We explained PV watts last week, Revit, and fCHART, because Revit is good for modeling. So we have an interface, we have the building there. Others, PV watts and fCHART, they don't have a graph. Well, they do have an interface, but you cannot model a building. You have to introduce data. Revit, PV watts, and fCHART, depending on what I want to do or what I want to calculate. But I was explaining before the brochures or the catalogs that I have uploaded. So this is a Chinese brand, YHI Power, with this nice Chinese logo. And the other one, I don't know where the other one is from. And Renochi. It sounds like Southern Europe, these kind of names. Anyway. No, so they are Philadelphia. Okay, so they are from the United States.
Is that Canada?
Sorry?
I think it is Canada because it says Ontario.
Yeah, it's Ontario. Philadelphia. It's Philadelphia Street, Ontario. Okay, so yeah, it's in Canada. Okay, great. From Canada. So we have two different PV panels, and probably I took this from my favorite website, Alibaba, and I took this from Amazon or something like that. But here we have data, and we have to trust on this data. And I was speaking about the NOCT and STC, probably in both. Okay, here we have the STC, and we also have the NOCT. Okay, so you see that this is something common, and we need to know what it stands for, because you will find this STC and NOCT in every single catalog, PV catalog that you can find. So let's find out. I think I explained this in in Building Science 1, but I'll do it again. STC PV panels. So STC stands for standard test conditions. Okay, so we are testing different PV panels. So that's why we want to compare a panel that I have downloaded from Alibaba and another panel that I have downloaded from Amazon or a Canadian website or whatever. We need to compare their performance, and that's why we have these standard test conditions. Both panels are tested at the same conditions. And what are these standard test conditions? The cell temperature of 25 Celsius. 25 Celsius is around 72 Fahrenheit or 70, let's see, Celsius to Fahrenheit. Okay, so it's 25 Celsius, it's 77, so it's more than I thought. Okay, so this is 77 Fahrenheit. Why? Well, this is all the panels in the world are tested at this temperature because the temperature affects the performance of the panel. So here we have the standard test conditions. There are other, yeah, so the irradiance is 1,000 watts per square meter. Well, this is too high. I mean, this is the maximum irradiance that we can have at a specific moment. That happens maybe once or twice a year. That means that the sun is completely perpendicular and we don't have any clouds. The air is completely clear. Okay, so that only happens, yeah, so maybe let's say twice a year. And well, probably in Saudi Arabia, it happens more than here. But anyway, this is very unlikely that it can happen. It's the maximum solar irradiance that we can have. We have a performance. What is the NOCT? NOTC, sorry. NOTC. Okay, so this is the normal operating cell temperature. So it's not test condition, it's CT. Okay, so that stands for nominal operating cell temperature. That means that if we look at these conditions, okay, the irradiance is not 1,000, it's 800, which is more feasible, more likely. It's a good irradiance. I mean, this is a clear summer day, but it's not 1,000. And then the air temperature is 20. We have wind velocity. Okay, so we have other testing conditions. More feasible, okay, because the solar irradiance and the temperature is not as optimum as, yeah, the cell temperature at NOCT is 50 degrees. The ambient temperature is 20 and the cell temperature is 50. And installation level, this is the 80, or they are different units, but this is the 800 watts per square meter. This is the energy that comes from the sun. So that's why when we look at the maximum power under NOCT, it's lower than the power under standard test conditions. Okay, so this is what we have to understand. Sometimes when we are making simulations, we have to introduce the maximum power of the PV panel that we are using. And the first thing we need to ask is, under standard test conditions or normal operating cell temperature? Well, I prefer this one because I have both. In this catalog, we have different elements depending on the size. So it's not just, okay, so here we have 15, 30, or 55. That depends, because here we have 3 different sizes. Okay, usually, well, for sure, the biggest one has the higher maximum power. And that's another interesting thing that we need to understand, the concept of Watt P or WP. This is the peak power. Peak means that it's the maximum power that we can get. So at the optimum sun tilt, at the optimum irradiance, this is the maximum power that we can get. So that's the concept of Watt peak. P stands for peak. R rated in one peak, sometimes kilowatt peak is used for peak and stands for peak power. This value specifies the output power achieved by a solar module under full solar radiation, under set standard test conditions. Okay, so the concept of peak value means that you are testing this under standard test conditions. So it's the best performance that you can have with this PV panel, which is, it never happens. I mean, or it happens 1 second a year. Okay, so we will never get, but if we want to compare 2 different panels or 3 different panels, we need to compare the same conditions. So if you test a PV panel in China, or if you test a PV panel in Canada, or if you test a PV panel in Italy, the performance is different. So you have to go to a workshop or a laboratory, and then you have to create the test conditions, and then you can test different panels under the same test conditions. Okay, so here we do have the module efficiency, 15.4. Okay, but sometimes we have different efficiency depending on the irradiance. Okay, so it's not complicated, because at the end, most of the panels are between 15 and 20. The efficiency of PV panels goes from 15 to 20. Closer to 15 is worse than closer to 20. What is the efficiency of this one? It's 19.18. So the Canadian panel, in this case, has more efficiency than this one. Okay, so you can use, if you are working with this assignment or the final project, you will have to select a PV panel, and we need dimensions. So here in these PV panels, you see dimensions, and we need the maximum power, and we need the efficiency of the here. So this one is 15, and the maximum power at STC, it's 250. Okay, that's fine. So this is the first thing we have to look at when we are analyzing PV panels. What are we doing now? Okay, so I'm explaining this. I'm explaining how to use the PV fCHART. And this is something that, for example, we don't have any information like this in Revit that I know of. And about the PV watts, when we are in PV watts, you remember, okay, so here we don't have efficiency. We have this standard premium or thin film. The efficiency of the premium is the best. The efficiency of the thin film is the worst. And here we have the DC system size. Okay, so we need to understand how we can work. So a standard, it means that it's an efficiency between 15 and 20. It can be 16, 17, something like that. Premium will be closer to 20. This thin film will be even below 15 because the thin film, it goes below 15. And then the DC system size, it has to do with this power. Okay, if you remember, if we are selecting this one, this is the one we selected last time. So if this is 320 watts, 320 watts at STC, then dimensions, it was this PV panel, dimensions, okay, 166, so 1.6 times 1. Dimension is 1.6 meters times 1 meter. So in square meters, this is 1.6 square meter. Okay. So what is the production per square meter? So it's 320 watts divided by 1.6 square meter. Okay, so we calculate this. This is 320 divided by 1.6. Okay, so it's 200 watts per square meter. And now what is the area of PV array? Let's say that it's 100 square meters. So what is the DC system size? It's 200 watts per square meter times 100 square meter. And this is 2, 1, 2, 3, 4. It's 2000 watts. In PV watts, remember that we have to use kilowatts. So this is 20 kilowatts. Okay, so if we have a roof of 100 square meter, and we are using this panel, this is the value that we need to get first, the watts per square meter. And we divide the maximum power at STC divided by the area of one panel. This is area of the panel. Then we divide this. This is the production of one panel divided by the area of the panel. So this is the production per square meter, per unit of area. And then we need, this is the project. This is the roof area. For example, it's 100 square meters. And then we need this. The problem is that in all catalogs that I know of, this is always watts. You will never find BTU hours here. It's very unlikely that in a catalog you find BTU hours. So you always need electrical units, which is the watt. And it's always about, well, here we have inches and millimeters or international units. But if you want to calculate PV arrays, you have to get used to working with both units. Well, working with international units. You can work with international units to calculate thermal loads. This is what we have been done so far. But if we want to calculate electricity, you have to get used to working with international units. But this is how we calculate the system size here. And that's how we can use PV walls. Okay, so here I explain again what the STC is, the standard test conditions, 1000 watts per irradiance, 25 Celsius for the temperature, and then we have the nominal operating cell temperature. Okay, so in this PowerPoint, you have the definition of both. Then we need to understand the layout, what we want to do. Usually, this is the most common layout, is PV energy plus energy from the grid. I don't know, I would recommend my clients do this. You have always the off-grid or the standalone system. That means that you need batteries and you don't have the grid anywhere. So you are in the middle of the forest, in a nice waterfront, 5 miles away of the next road. Okay, if you want to live like that, that's great. Live free or die. But if you, I don't know, I wouldn't do this maybe because I'm a coward, but I wouldn't do that. So I will rely on the grid just in case if something happens, I'm not without any energy. Okay, so I can generate my energy with a PV array, and then I power my equipment. It can be the HVAC system, it can be the computers, it can be the electric lighting, whatever. And if something happens here in the event that I have an outage of PV or it's snowing and I can't generate any solar energy, I always have the AC main supply. If you go for the standalone or the off-grid system, you need batteries and you depend on batteries. If you want to imagine that then you have to calculate where you are. So what is the maximum time that your PV panels won't be generating electricity? If it's snowing here, maybe you can generate electricity for 2 days, 3 days, a week, 40 days. I know. Then you have to size your batteries accordingly. Sizing batteries are extremely expensive and they take up a lot of space. So that's it. If I'm designing a PV array in the south of Spain, so there are years in which you don't see any clouds. So your batteries will be quite small. But if you are designing an off-grid PV array here, I don't know, I'm not used to this weather yet. Well, I know it's always bad, but I don't know how many hours without sun we can have. 3 days, 4 days. And I would rely on this. There is always something in the middle. You can have grid and you can have batteries. This is the most expensive, probably the most reliable schematics or the most reliable layout. But these are the two options, either without batteries and taking energy from the grid if you don't have enough power, or standalone and relying on batteries. And then you can always have something in the middle. So you have the batteries and you take energy from the grid in the event that you run out of the energy on your batteries. But this is the first decision that we have to make, and we have to talk to the clients because I don't know what their way of living is, but it affects the way of living. If you can, well, if you have this, you can have a backup generator. I don't know. You have to talk to the clients to see what they want to do. And then the second thing we have to do is to understand the energy consumption, the electric consumption that we have. We can have the heat pump if our heating system is an electric system, like this building. In this building, we don't have a boiler, we don't have gas, we don't have oil, so everything is runs on electricity. Again, that's another decision, because probably electricity usually it's more expensive than oil or fuel. Usually, maybe it will change in the near future. We don't know, but it makes sense because fuel, you burn your fuel and you generate energy. In electricity, you have to burn fuel or you have to generate electricity somewhere, and then you have to transport this electricity to your site. So in terms of production, transportation, electricity, unless you generate your own electricity on site, it's more expensive, because first you have to transform something into electricity, and then you have to transport this electricity from the energy plant to your house. So it makes sense that it's more expensive. Anyway, that might change. Maybe in the near future or in 2030, we won't have fuel anymore, and everybody will go solar. I don't think it might happen, but if it's not in 2030, maybe it will be in 2050 or in 2099, or maybe it will never happen. We don't know. And nowadays, the world is becoming more and more and more renewable and more solar. So this is the trend right now, and there are good reasons for that. But we don't know. Anyway, we need to understand the devices that we have in our house and what is the maximum consumption of, or the consumption of those devices. And then we have to generate like a table. When are we using the heat pump? Well, we are using the heat pump, the AC, the cooling system in summer. How many hours a day? 3 hours a day, 4 hours a day, 8 hours a day. How much are we using the water heater or the clothes dryer or the dishwasher or the space heater or the hair dryer or the refrigerator or the computer? Well, it depends. The electric demand is growing. I mean, we have more and more appliances, and most of the appliances run on electricity. So we consume more electricity now than we consumed back in the 80s, in the 1980s. So we have to be aware of that. And this is the first thing. That's something else that we have to talk to our clients. We cannot decide, okay, so you won't have a hair dryer. It's forbidden. Why? Because it consumes a lot. Okay. No, it's up to our clients, so we want to talk to them. And well, I always show this. There are devices that consume very little energy, but they are on a long time, like lighting, electric lighting. It's on, especially if it's winter, so we can have 12 or 13 hours of artificial lighting. On the other hand, we have the cooker, which consumes a lot of energy, a lot of power, but how long is it used? I don't know, for a couple of hours a day, or even less. Okay, so you have to keep that in mind, the consumption of the device, and then how many hours you are using this device. Something critical is the freezer or the fridge, because it consumes a lot, and it's always on. Okay. Yeah, so this is the first decision that we have to make. We're not to make that decision today, but for the final assignment, you will have to make assumptions and just let me know. I will accept everything that it's feasible. If we're analyzing the TDS center, we don't have a cooker that I know of. Do we have a cooker? Do we have a washing machine or hair dryers? I don't know. Okay, so you have to analyze the building. Do we have lighting? We do have electrical lighting. Do we have televisions? Well, we don't have television, or maybe we do have, but we do have computers. How many computers can be on at the same time in this building? We have to find out. We have air conditioner. Yes, we do, because and we have a heating system. We have an electric heating and cooling system. So probably we have to calculate this beforehand. Okay, so if we are analyzing this building, we have lighting for sure. We have computers for sure. We have the heating and cooling system. And what else? Okay, so let's we will find out, but for sure we will have lighting, heating systems, and computers. And then we need to create this. We need to create like a electricity demand in kilowatt hours on a monthly basis. Okay, so we need to understand what happens in January, in December, and when we have the peak consumption. So there is a peak consumption in January, and there is another peak consumption in July, August. Will it happen in this building? Probably not in July, because in July, is this building occupied in July? We don't know. Last year it wasn't, for sure. We don't know. Okay, so we have to analyze this. In single family houses, if you are living in a single family house throughout the year, this is the typical load profile. We have a huge consumption in January, February, December because of the heating system. And then depending on if we have a cooling system, there's another peak at July. If we don't have this cooling system, probably we don't have this peak in July. But this is something that we have to analyze in each building we are designing. So there's not a pattern, but we can have a pattern for single family houses. Okay, so we have a pattern of consumption. Office buildings, we have a pattern of consumption. But educational buildings, it depends. If there are summer courses, there will be consumption in summer. If there are no summer courses and the building is closed from July till the end of August, okay, so we won't have this peak here in summer. So we have to analyze three different things. So I'm going to summarize this. One, PV array. So we need to understand what the PV array is, and yeah, how many panels we need, what is the performance of the panel. Second, the PV or the energy system. In the energy system, there are two options. There's always something in the middle, but we have we can have connected to the grid, or we can have the off-grid system. Okay, so there are these two options. Then analyze the building. In analyzing the building, we need devices, we need schedule, and that's it. Okay, if we know the devices that we are using and we know the schedule, when the building is operating from 9 to 5, from 6 to 8 p.m. or 24 hours. So we need always the devices and we need the schedule. So this is what we need before starting analyzing anything. We need to analyze, or we need to answer these 3 points. And the PV array, well, it's something that depending on the providers, we need to ask the providers about the specifications of the PV panel. The PV array includes the panel, includes the area, the tilt, orientation. This is what we have done so far with Revit and PV watts. Okay, so we can understand okay, what area or what tilt or what orientation is the best? Or we have different options, and then we make a decision. This is the design of the building, and then we decide on a panel, and we calculate the PV production. Then we need this. We need to understand what we want. Do we want batteries, or we don't want batteries? That's a huge decision. And finally, we have to analyze the building. What are we using there, and what is the schedule of that building? Okay, so before anything else, we have to start by answering these three questions. And each question has other questions, like what panel are we using, what area are we using, what is the angle, what is the orientation, and then the energy system. Yeah, and okay, so this is the first three things that we need to prepare when we are preparing a report on PV panels or PV array. Okay, so once we have this, what would I do next? I would work with Revit. So you know that this TDS 360, it's on Canvas. And on Canvas, I have uploaded a lot of things here. So you have to download. I have uploaded this Revit family. So this is a solar panel. It's just to make it nicer. I wish I could work with this PV family when it comes to energy production, but it's just aesthetics. So it's just to, if you don't want to have a flat surface and you want to have something that looks like a PV panel, you can upload this. And then you have to work with the brochures. Okay, so this is the building that we are using. And I started last week, I started defining this building because the original file is just the building itself, but now we have to design this PV array. So we're going to do this quickly. And well, you have to look at this. So first, you know that there's like a structure. If you walk around the building, you see that structure. Okay, especially if you walk Winchester Street, you will see these columns here. Okay. How many of them? That's why we have to analyze the levels, and matching on these grids. We have these elements. Okay. I can show you how to do this easily. So let's work on grid. Okay, yeah, I have designed this on grid 6. Now I'm going to work on grid 5. So imagine that we are working from the west. Yep. And I want to do the same shape here. So this is the structural element, the main structural element. So I can create a component, model in place. It can be structural framing because this is a structural element. Okay. I would use extrusion, and then I would set grid 5. Okay, so it has to be one of the grids. And then I can trace this here. There you go. Now I go to the 3D model, and it's here. Well, let's go to level 5, and I have to make it so this is a structural element. I finished the model, and now on the 3D, I have to. Well, that's a good question because depending on the shape of the building, I don't have this element here. Okay, so probably I need to change that shape. So I go back to the west elevation, and I have to edit in place, edit extrusion, and then I need to move this inside the building, and then I click finish and see what happens. Not yet. Edit in place, edit extrusion, select these two elements and move it inside the building. There you go. Okay. Yeah, so we have to design like a feasible structure and not, but just make sure that at these elements we have a structure, or at these grid lines we have structural elements. And then, well, I have inserted this panel. You can just drag it here. And this is the family. Unfortunately, we can select this, but if we want to run solar analysis, if we want to analyze solar, we can't select this. You see, we can select this element, but we can't select this to create the solar analysis. It's a shame, but we can't. So this is just for aesthetics. So we have to carry out the solar analysis with this roof, and then we can insert this just to make the drawing nicer. Okay. And when we are, we know that copy. Okay, we always need a space between these two panels, and we would need a space here as well. See what I'm doing. Okay, and finally we have to work with all these panels there. Okay, so it's just to make the drawing nicer. It will look more professional if you do this with the panel. And then we need to understand the construction of this. So as you can see in this family, we have the panels, and this is like a beam system. Okay, so we have this element, and this element has to rest on some structure. So if we go to the west elevation, yep. So you see how these elements they have to rest on a structure element like this, and we would need to copy this here. Okay, so we need at least two elements there. This one. This one. I will copy this one here. And here. And now I can copy everything, this family, this, and this, copy, now copy multiple, and last one, no, last one doesn't fit here. So you can see that sometimes, although we have all these roof area available, we can't use all these roof area, or at least we have to think of a different way to place it, or we have to extend, I don't know, but sometimes we cannot place all the panels that we can place because of the constraints of the shape. Anyway, you have to do something like that, and at the end you will end up having all these rows and all these panels. And but the area, you can use this area. Okay, so if we are doing this, you can use the area of this roof. Here we have in square feet. If you want to know the area in square meters, you can always use this option. Okay, and here you have the square meters selected. Okay, so this is when it comes to the model, you have the building, but now you have to design your PV array. Keeping in mind that the PV array, the structure, has to match these grid lines, and then you have to place this family of PV panels. No, maybe I would select all of them. Including the structural element. Yeah, the problem is this. We could move them down. But now how do I hold these elements here? Okay, that would be a structure. We'll find out. Anyway, try to at least work with these elements because those elements are fixed, and then we will have to figure out how to do that for the other structural. I will make up something to make it feasible. But if we have these constraints, we need structural elements going here. Okay, so we need to rest this element on something structural. Okay, so this is the typical open rack. It doesn't have a tracking system because they are fixed, but try to place as many panels as you can on this roof area. That's the challenge. So make sure that they fit here, and you make the most of this area for the PV arrays. Okay. So I'm going to write down the analyze solar. Okay, so it's 1,140. Okay, let's say that we are, because there is always something, there's a gap between two panels, so we cannot have 1,149 square meters. So let's say that we have 1,100, something easy to remember. So our PV array And now we can start answering these questions. The PV array, the area is 1,100 square meter. What is the panel? The panel is this that we have decided here, is 320 as STC, and the dimensions, it's like this. So the panel production is 200 watts per square meter. What is the tilt? I think we measured the tilt last time. If we go to the west elevation, we can always annotate angular, and from this to this. Okay, so the tilt is 15 degrees. 15. And the orientation, we found out that it wasn't exactly south. Okay, so let's say that it's south for the sake of listing. Okay, so this is the first question. What is the watt per square meter of our panels? We did it before. We have this power at STC. We have the area of the panels, and then we have to calculate the power per square meter. Then what is the area of the roof? The area of the roof is 1100. What is the tilt of that roof? 15. The orientation, it's south. And now the energy system, grid or off grid, we are going to use the grid one. So I'm using Revit. With Revit, I select the area, the geometry. I'm using the catalog with this and with the dimensions. And now I'm going to start using the third software, which is the PV watts. No, the PV watts, not, sorry, the fCHART. The fCHART, that makes sure that you go to programs and you select the PV fCHART, not the fCHART without PV, but just the PV fCHART. And we launch it. Okay. So now we're going to analyze this software. First, here we have the system parameters and the economic parameters. Let's close the economic so far. We are going to focus on energy. How does it work? Well, we can go step by step. So let's look at the first window we have here. So the city. This is a demo version. It's not the full one. You can pay for it if you want. I do not object. But if you want to use this here, this is created in the United States. And we have different areas. We have Northeast, Northwest, South Central, Southeast, Southwest, Upper Midwest. Well, if we're in team, I would select Northeast. Okay. We cannot select the, or maybe we can, but we have to look for it. Okay. So let's select Northeast, and that would be fine. So we're in Northeast. What is the cell temperature at NOCT conditions? Okay, let's find out because we have this information in the catalog. Nominal cell temperature at NOCT conditions. It's 47 plus minus 2. Okay, we can type 47. By default, it's 44, but in our case, it's 47. What is the array reference efficiency? They start with 10 or 0.1. It's very low efficiency. Our efficiency, according to the catalog, was 19. Okay, so we can type there 19 or 0.19. What is the array reference temperature? Do we have this? the array reference temperature? Well, we don't have this information. If we don't have this information, we'll leave the default, and that's it. What is the array temperature coefficient? We do have this. This is 4.3. Well, it's times 1,000, so it's 4,300. But here, you see that we have the temperature coefficient of maximum power, and this is 0.47% times 1,000, so that would be 4.7. So this is 0.7 or 4,700. The power tracking efficiency, we don't have a tracking system, so we can type 0. The power conditioning efficiency. Okay, so let's say 0.1. We cannot type 0, so let's say 0.1. And okay. So here we have the array area, number of panels times the panel area. So if we want to be accurate, here we can type either 1,100, or if we want to be extremely accurate, you can count them. Okay, you can say 1, 2, 3, 4, 5, 6, 7, 8. I don't know how many times the area of each panel, and then you can go for it. I wouldn't do that, so I would, because we have deducted. We have deducted some area from the roof. So here I would say the array area 1,100 square meters. The array slope, it was 50. And the azimuth, south is 0, so we can stick to 0. The most important things are the location. We have to select northeast, the area, the slope, and I would say the efficiency. Look at this. They are not asking about the power of the panel. Well, with all these parameters, they calculate the efficiency of the maximum power that this array can produce. Okay, so there is no what is the peak power of the panel? No, they ask for the efficiency, they ask for the reference temperature, they ask for the cell temperature conditions and all that stuff. And with all these values, they calculate the efficiency. They are not asking for the peak value. Okay, so this is the first window. Now we have to go to edit, preferences. Okay, in preferences, we have international units or English units. I would say international units. System. Okay, the system is the second question, the energy system. This is a flat plate array. Okay, so let's analyze this first. We have these 4 options: flat plate array, CPC, or axis tracking or 2-axis tracking. We don't have a tracking system, so we are not selecting this one. And what's the difference between the flat plate and the CPC array? Well, the flat plate is the traditional, this is a flat plate array. And if we want to find out what the CPC array is, so it's not flat. As you can see, we have like this circle, and here we have another cell, and it's about reflection. Okay, it's different, so it's not the same technology. Is this better? Probably that would be better. I don't know. 90% of the panels that we can purchase are the flat panels. This technology, well, maybe it's interesting, and maybe I'm sure it's more efficient because it works with this and it reflects all this energy into that point. So I'm sure this is more efficient. but I don't know. I don't know anything about this technology. I have never used this technology. I don't know the prices. Okay, it's not. It's a different technology. So in this course, we're not going to use this kind of technology. But the system, we can decide. If we don't have a tracking system, that's fine. And I would use a flat plate. Okay. This is the standalone battery storage or utility interface. So the standalone is the standalone system, off-grid, only batteries. The battery storage, I think it's something in the middle. We have a battery, but we are connected to the grid. And finally, we have the utility interface. It's a system that it's only connected to the grid without any batteries. I would use this one just to start analyzing something. Okay, so let's move to flat plate array and utility interface. Now, on weather, select data location, it's the same here. If here we have selected Northeast, we will select Northeast here. And the most important thing, well, the most important, something that we have to look now, because this is the third question. Okay, so we have selected the energy system, the grid. It can be flat, or it can be PCB, flat. Or we can have a tracking. Are we connected to the grid? Is it flat or PCB, or do we have tracking? Okay, so these are the three questions that we have to ask. And finally, we have to analyze the building demand. And this is the load. In the full version, you can save load files and then you can upload it. In this version, we can change the load. Unfortunately, we cannot save it, but there's something else we can do, and probably we will end up doing. So look at this. Here we have the load in January, February, March, April, May, June, okay, on a monthly basis. By default, all months are the same. And we have this option, change all. And here we have the time and the load, okay, from 0 to 1 until 23, 24. So this is 1 day. Okay, so as you can see, this is very accurate because it's okay. Our building starts operating at 6 a.m. Okay, so we can type that all this is 0. And at 6, it starts operating. And then as of 8 p.m., it's 0 again. Okay, so we need to know the schedule. And then from 6 to 6, so every hour, we can decide the demand in watts that we have in our building. So that's why we need to calculate thermal loads. Thermal loads, the heating and cooling system, and we need to know the devices and how many hours we are using this device of the day, because we have to heat up the building. Probably in March, April, or May, we don't have the heating system, or probably in June and July, we will be using the cooling system. And we can know the schedule. Okay, so if this is an office building, there's a break for lunch from 12 to 1. So maybe here we can lower this consumption here because we have a break and only a few people remain in the building. Okay, so we can be extremely accurate. We can do this on a monthly basis every single hour. Okay, so the more accurate we are, the better the result will be. We cannot do this with PV watts. We cannot do this with with Revit. We can work with schedules. Okay, but here we can work with schedules. So we can say okay, and this is the demand. And finally, we can run, we can calculate, and that's it. It doesn't take any time, so it's already calculated. Ahí va. Where is it? Here. Okay, so here we do have the summary month by month and hour by hour. Okay, so you say in February from 10 to 11, am I selling or am I getting energy from the grid? Okay, that means that if you sell, that means that you have an excess of energy that you are generating. And if you buy, that means that you need to take energy from the grid. Okay, so here from 6 to 7, we need to take energy from the grid, but the rest of the time, we are, well, at the end of the day, we are getting energy from the grid. But here, we are selling energy. So we are covering the 100% of the demand, and we are selling an excess of energy. Is this happening? Because we are using this area, so we are using the area of this building, and probably the load is for a single family house. This is what will happen. If we increase that load, imagine that we are adding a zero to all the loads that we have here. We click OK, we calculate it again. Okay, so now we are not that optimistic, and we are, as you can see, we are taking energy from the grid many times. Okay, so that depends on the demand, and that depends on the array. I would use the summary so far. Okay, so going month by month, it's too much. So I would go to the summary, and this F value is the percentage of the energy that it's covered in this month with the PV array. Okay, so in January we cover 49%. In July we cover like 83. In June 84% of the array. This is the energy that we are generating and we are not using, and this is the energy that we have to buy from the grid. Looking at this, this is the yearly the yearly summary. So we are selling more energy than we are getting. So I think that would be a good business. Okay. Because we are not generating 100%, but there are moments that depends on the schedule. There are moments in which we are generating more energy than we are consuming. Because we are not using that energy for the building. The problem is that I don't have any batteries, so when I'm generating a lot of energy and we are not consuming it, I have to sell it. On the other hand, there are times in which I'm not generating all the energy that I need, and then I have to buy it from the grid. But the balance is positive between the energy I'm selling and the energy I'm buying. Okay. Yeah, so analyzing this month by month, hour by hour, well, we have a lot of information. And we can plot. We can use the parametric plot. And we can, for example, compare the energy that we are selling and the energy that we are buying. So let's do this. Let's click OK. And then let's plot the energy we are buying. but this is cell temperature at N-C. I don't like this. So we can, yeah, so let's use the monthly plot and let's use the sell and buy. Okay, so this is the energy I'm selling. For sure, I'm selling more energy in summer than in winter. And then I can plot the monthly plot, the energy that I'm buying. Okay, so I'm buying less energy in July because I'm generating more energy. Okay, so by comparing this, we can have a lot of, and now we can print it. As far as I know, monthly plot. Print. Okay, so here you can print either plot 1 or this is plot 3. Print, and you're generating a PDF document. Let's okay. So we have a nice report with plot 1 and all these values that we have generated from that report. Here we have the Northeast, all these elements, the area. Okay, so everything that we have done, and this is the economic summary. That's interesting because if we look at this and we look at the cash flow, okay, so we have this analysis in 20 years, and when the cash flow, well, I don't know. We will analyze this because we can understand when we start making money. So we have to pay money up front, and then we start generating money from our grid. Okay, we are not going to analyze economic results, but with this cash flow, we will understand as of this point. Okay, so as of the year number 10, we start making money, and the investment has been. This is the payback period. Okay, so I have pay money up front, and then as of the year number 10, I start receiving money because I have already generated all the energy and I have saved all the money that I have paid up front. Okay, so we're not going to do this today, but with PV watts, with fCHART, we can do this. With PV watts, we can't. With Revit, we cannot do that, as far as I know. Okay, so in this fCHART, we can be very accurate because we have a monthly summary that I can analyze what happens on a day, on a specific day in every single month. Okay, so it's very useful. The problem is that maybe it's too much information. That's the only objection that I have with this software. But with this monthly plot, you can plot, for example, F. F is the percentage of the demand that you cover. Okay, it seems the same graphic, but it's not, because in January we only cover 50% of the demand. In December it's 40 something, and in June, July is almost 90%, it's more than 80% of the electric demand that we are covering. Okay, so we have a lot of information, and the good thing is that we can print it. And if we do have a PV can we edit this? No. No, I don't have the Adobe Acrobat, but we can easily turn this into an Excel file. And this is something that we can use in our Excel file, all these things. And we can prepare nice charts and a good report. But even just printing this, it's a nice report. And the more things you print, so here we have plot 5. What else can we plot? The load. Okay, so this is the load. This is the electric load that we have in our building. In February, we always have less because we have 28 days. Okay, so that depends on, this is 31 days, 30, 31, 30. This is July and August. Because we have fixed, if you look at the load, it's the same in every single month. But we can make it different. Okay, so it takes a lot of time. If we are accurate with the loads, it takes a lot of time to fill all these charts. The good thing with the full version is that we can do this once and then we can save it. The problem with this version is that we can't save. This is the demo and cannot be saved. So we can do it and then we have to do it again. Problem. But if we print, we can print all these plots. We can have the economic output, weather data. Yeah, so let's print everything and see what happens. Number 2. Okay, we have a long report with all the graphics that we have generated, which is useful. Okay, this graphic is interesting because this is the demand and this is the energy that we are generating. Okay, so here we are almost covering the demand, but here we are at 50%. Yeah, so comparing the demand with the actual production, it might be interesting. And here we have month by month, what happens from 0 to 1. Okay, so that depends on the load. So basically with this, we have a lot of information, and do we need all this information? And we have the economic parameters. We haven't talked about the economic parameters yet. We have talked only about the energy parameters. Anyway, now the challenge, and probably this is up to me now. I have to make you understand what we are doing. Okay, so we have these three tools. We have Revit, we have PV Watts, and we have fCHART. Now we have to combine the three different software tools. So there, by answering these questions, we can. So probably we need to answer these questions with Revit. This is up to us because it's about the energy system, and then the demand. It's something that we have to enter when we are using the fCHART. And why are we using PV Watts? I would use PV Watts just to check that what I am doing is what it's feasible. So it's like a check that the results that I'm getting from PV Watts or from fCHART are accurate. So what would that be? Let's use PV Watts. in PV watts, we can be accurate with location. In fCHART, it's just the Northeast. Here we can select Keene, New Hampshire. Okay. So I can select the tilt is 15. I can select the azimuth is 180. And I can select the DC system size. What is the DC system size? This is what we need in fCHART. But what is the DC size in PV watts? It's 200 times this. Let me see. Okay, so it's the watts per square meter times the area. So this is which number? It's 200 times 1100. Okay, so it's 2,000 and 20,000 is 220,000 watts. In PV watts, in kilowatts is 220 kilowatts. Okay, so the size of my array is 220 kilowatts. The tilt is 15, module type is standard, this is an open rack, the azimuth, and then we calculate this. And now let's compare this okay. So what can we compare here? Oh, it's not clear. Because here we have the AC energy, so this is the energy that we can generate with our PV array. And here we have the solar, but those numbers are not alike. So probably we are comparing different things because none of the columns match. Yeah, so I can see this is 15,000. And this is 64,000, and this is 551. So none of these numbers match. So that's another thing that we have to find out. Because the other thing we can do is with Revit, I'm going to calculate the solar energy annual PV. I'm going to select this surface. I want to create a PV energy, and I can update. Okay. The challenge now is that we have to compare the results that we are getting for 3 different software. And what are we comparing? Okay, I think this is the total PV energy production is 233, and the yearly, this is 268. This is 268,000, and this is 233,000. So these two values are fine. Okay, so this is PV watts, this is Revit, and this is fCHART. So what can I do with these values now with fCHART? I don't know, but I have to find a relationship between these 3 software.